In this video, we'll go through some of the questions from Unit 1.2. We'll begin with question 8. In your car, you covered 2 meters during the first second, 4 meters during the second 1 second, and 6 meters during the third 1 second, and so forth. Was this motion constant acceleration? So what I'm going to do to try to figure this out is I'm going to make a table. And I'm going to start with time, and I'm going to assume that the object begins at a position of 0 at a time of 0. I'll also put a number line down here to help with my thinking. So the object started here at 0 seconds. Then after the first second, we covered 2.0 meters. Okay, after during the second, let's see, 4 meters during the second means that we're going to go an additional 4 meters, which brings us to 6 meters. And this is at the end of the second, at the end of 2 seconds. We will have gone 6 meters. Again, this distance is that 4 meters that we went during the second. And 6 meters during the third second. So 7, 8, 9, 10, 11, 12. So that's 6 meters. That takes me out to 12 after 3 seconds. So now the question is that constant acceleration? So what I'm going to do is I'm going to solve for the acceleration in each of these, at each of these times. So assuming that initial velocity is 0, we know that displacement is equal to 1/2 a delta t squared. And then if I solve for acceleration would be 2 times delta x over delta t squared. So the acceleration here is not relevant because the object hasn't started moving yet, but after 1 second, acceleration would be 2 delta x over delta t squared, or 2 times 2 over 1 squared, or 4. Okay, now I'm going to do the next one. Acceleration over the interval would be 2 times 6 over 2 squared, and that's 12 over 4, and that's 3. So already I can see that the acceleration is not uniform over this entire thing. And I can do the third one if I like. 2 times 12 over 3 squared is 24 over 9. Again, that doesn't equal 4 or 3, so the motion acceleration is not constant. Okay, let's look at another one. I'm going to snip it. Let's look at question 9. Oops. Oh my goodness. Okay. Object 1 traveled at velocity v. Object 2 traveled at velocity 2v. Compare their distances that they cover in time t. So here, what I'm going to do is I've got 2 objects, and I really want to consider what's happening for each one. So object 1 has a velocity, which I'm just going to call v, and object 2 has a constant or average velocity, which I'm going to call 2v, and we'll put subscripts to indicate object 1 and object 2. There's only one formula I can use for constant velocity motion, and that's displacement equals velocity times time. So for object 1, the displacement is going to be velocity times time. For object 2, I'd use the same formula. And then I am plugging in values here. So the displacement of object 2 is going to be 2v times delta t. Then to compare, what we could do is we could make a ratio. We could say, what's the ratio of the distance or displacement of object 2 over the displacement of object 1? And object 2 is 2v delta t, and this one is just v delta t. And the v's cancel and the t's cancel, and I just end up with a 2-to-1 ratio. So I would say that displacement of object 2 is twice or 2 times the displacement of object 1. Let's look at another. I don't understand why it pastes it so small. Okay, there we go. Object 1 has initial velocity v, slows to a stop with acceleration a. Object 2 has velocity 2v, slows to a stop with acceleration a. Compare the stopping times and then compare the stopping distances. Okay, so same idea. Object 1, object 2. Now these objects are slowing down, so that indicates acceleration. And to consider what's going on, I want to make sure that I've got my kinematics handy. So write down those 4 kinematic equations and have them handy on a note card or something. I'll have to scroll back and forth. So object 1 has an initial velocity, which we're going to call v. And object 2 has an initial velocity, which we're calling 2v. They both slow to a stop. So their final velocity of each of them is 0. The acceleration is the same number. And now we want to find stopping times. So I look at my variables, v0, v, a, and t. And that takes me to this formula. So I'll write out the formula. And I'll rearrange the formula to solve for delta t. And then I'm going to plug in for each object. So for object 1, v is 0. The initial velocity is v, and acceleration is a. So delta t is negative v over a. And for the other object, v is 2v. Whoops, I got mixed up. Sorry, v is 0, again. The v0, the initial velocity, is 2v, and the acceleration is a. So t1 is negative v over a, t2 is negative 2v over a, and again, we can see that t2, trying to go too fast here. T2 is twice T1. Okay, next we're supposed to look at the stopping distances. So what I'm going to do in Notability is I'm going to take a little shortcut here. and I'm going to find the stopping distances. And the equation that's going to work for me this time with initial velocity, final velocity, acceleration, and delta x is this one. So I'm going to write that. I'll write it twice, once for each. Helps me memorize it as well. And then I'm going to plug in what I know. So the final velocity is 0. The initial velocity is v. Acceleration is a. And delta x is what I don't know. And if I were to solve this for delta x, I would subtract v from both sides and then divide both sides by 2a. And so I would get that delta x is equal to negative v squared over 2a. Okay, now let's consider what happens when we double that velocity. I've plugged in 2v instead of v, and I need to make sure to square the whole thing. So it's 2v squared in parentheses is 4v squared. And what I'm going to wind up with when I solve for delta x is negative 4v squared over 2a. And when I compare these, what I see is the v squared over 2a part is the same, and what's different is this negative 4. So the second displacement is 4 times the first displacement. Okay, let's do one more together. Let's look at number 11. Okay, object 1 has initial velocity v, so I'm going to start right in this time. Object 1 has initial velocity v. It slows to a stop with acceleration a. Slows to a stop means its final velocity is 0. Object 2 has initial velocity v. It slows to a stop with acceleration 2a. Again, slowing to a stop, so its final velocity is 0. Compare the stopping times. This is very similar to 10a. In fact, if I go back to 10a, I solved for delta t. I'm just going to go ahead and borrow that. So I'm trying to find T1 and T2. So I'm going to plug in what I know. T1 will be 0 minus V over A. T2 will be 0 minus V over 2A. T2 is half of T1. Okay, and then we're supposed to compare the stopping distances. So I'm going to start with the same knowns. And I'm going to go back to question 10 and borrow my hard work here. I solved for, I figured out which equation to use. It was this one. And I'm solving for delta x. So to solve for delta x, I would subtract v naught from both sides. So I get v squared minus v naught squared equals 2a delta x. So delta x is going to be v squared minus v naught squared over 2a. Maybe you can start to see what's going to happen here. The thing that's different is I'm going to divide by 2a, which means the stopping distance is going to be half. But I'll continue here. My stopping distance of object 1 is going to be 0 squared minus v squared over over 2a. And my second object is going to be 0 minus v squared over 2 times 2a. So I had to plug in 2a for a. So my second displacement is half my first displacement. Okay, I hope that helps. Please reach out with questions if you need to.